Thank you. I am, could you hear me? Okay. I am Tongfei Chen. I'm a PhD student at Johns Hopkins University working on natural language processing, a branch in artificial intelligence. So this is my sideline project. My advisor is actually not happy with me spending so much time on this. So let's look at what is deep learning, this recent AI hype that everyone is talking about. Basically, it is the core data structure in deep learning is tensors, a fancy mathematical term, which is basically a multidimensional array. In Python, people call it ND arrays. So, for example, an image is a 3D array where there are 3 dimensions: the width, the height, and the channel being the red, green, blue, 3 colors. And so an image could be represented as a 3D tensor like this, where every entry in this array is the luminance or in that color. This is in computer vision. Or in natural language processing, a sentence like "the cat sat on a mat" would be represented by a 2D array where the first dimension is the word and the second dimension is the embedding, where embedding is the so-called word embedding in natural language processing means every word is going to be mapped to a finite dimensional vector. So a sentence could be thus represented as a sequence of vectors like this. So basically every data structure that every thing in deep learning is the objects, be it sentences, videos, or like images, whatever, they're represented as a tensor. This is like a modern image classification network that given an image as input, output what kind of things it is. So this image recognition task. This is a fairly modern neural network where we first take a convolution network, rectifier linear unit, pooling, convolutional pooling, and flatten and fully connected layer and softmax, and then we output something. This is highly compositional. As just Runar said a few minutes ago, every deep learning program like this is a compositional program. If it is not compositional, we couldn't reason from it. Actually, I want to cite one of our professors at Hopkins who once said years ago on one of the conferences, says, "The world must be compositional or there's a God." So deep learning is basically function fitting. So let's start from the simplest case, where it's a linear regression task, where we are learning a function from m-dimensional vector to an n-dimensional vector, and a function takes the form of a matrix multiplication and a vector addition. So this is the simplest case. Or a more complicated case that people are familiar with is machine translation, where we train a function that turns a French sentence into an English sentence. So like this. So this is linear regression. So x is a variable and a is a vector, and we multiply them with matrix vector multiplication and add with b. So get us to y hat, was the estimated y, and this is the function f. And then, yeah, this is just a function. So the model is just a function to fit, is composed from smaller building blocks with parameters, and is trained by gradient descent with respect to a loss function. The loss function usually employed in linear regression is the so-called L2 loss, which is the square distance between the expected value y hat and the real value y, and the gold value y, we call it. So y is the gold answer, y hat is the predicted answer, so we got the loss. So we want to minimize the loss. So this is the whole function of x and y, xy pairs as input, and we train the parameters a and b to minimize loss L. LeCun is a professor at in New York University. He just said on his Facebook post that deep learning vive differentiable programming. So a better name for deep learning might just be differentiable programming. This is a program that's differentiable. So there's a lot of common deep learning libraries right now. So there's been a surge of these technical effort. By Google, there's TensorFlow, PyTorch from Facebook, MXNet originally from a bunch of PhD students at Amazon, Carnegie Mellon and University of Washington, then acquired by Amazon, Dynet from Carnegie Mellon, Cafe 2, originally from Berkeley, acquired by Facebook, and then Trainer from a Japanese company. These are a lot of common libraries that are currently widely in use. What is the problem with all of these? They're all in Python. So their current APIs in Python. So that's just a very sad thing. Let's look at why this is bad. So the Pythonic way that, so the Python people, they somehow developed a cult around themselves. They call themselves Pythonic. TensorFlow, let's take TensorFlow as an example. People use it a lot because it has the Google aura around it. So let's first start a placeholder, a tf.placeholder, and then we specify its type by a object in it. It's just this is how things are done in Python. So this is an x. So this is a node in the computation graph, x, and then y is another computation node, y here. So these are m-dimensional and n-dimensional. So a is one of the parameters we have. It's just initialized as a randomly distributed normal variable, and b. And then we start to compose to construct the computation graph. So ax is this node, predicted y is this, and then y hat. So cost function, here the final loss is just the predicted y minus the gold y, and then tf.power actually is element y's power. So in Python, people like to use for example, if we want to map a function over a tensor, they just write that function over the tensor. They don't differentiate between element-wise application and just application on a single value. So this is how it's written in TensorFlow. We see here that everything is just untyped. Everything is just going to be a tensor or just a node in the computation graph. Okay, so a more complicated example is in PyTorch. This is actually code I wrote when I was doing research. I'm, as a static typist, I'm using Python 3.5 above that has type annotations in here. But yes, it's still, the self.embedding layer X gives us a three-dimensional tensor, which I couldn't remember. I write it here. And there's a transpose function, transpose 0 and 1, means we swap the axis of 0 and 1. So, but this type change is not reflected in the type, so it's still a tensor. And we also have like things like unsqueeze, which means to add additional dimension in the first place of the, for example, this tensor has dimension 0 and 1. We add a 1, so it became a three-dimensional tensor with a first dimension of size 1 on squeeze, and there's expand. All these operations changes the shape of the tensor, of which type is not reflected at all. So for me, I need to write all sorts of comments in here, but normal Python people, they just don't. So yeah, they can remember these by heart. So let's see, what is the problem with the Pythonic approach? Everything just belongs to just one tensor called tensor. This is some bad practice from NumPy, which I think the root of all these evil comes from MATLAB. I'm not sure. So vectors and matrices, sequence of vectors, sequence of matrices, images, videos, words, sentences, these are all just one type tensor. So how many axes are in one tensor, the size of it? What does each axis stand for? So each axis has a implicit semantic in it. So what does this axis mean? What does the second axis mean? So it's not written in a type. So programmers have to track the axes and shapes by themselves. They have to remember them by themselves. Pythonistas, they can remember them by heart. I cannot. I as a static typist, I have the types to guide me. So I feel bad when writing all these. Let's rechant Northeast Scala's model here. Give me type safety or give me death. So let's introduce my attempt at creating a more type-safe deep learning environment. I call it Nexus, so you can check up here. So our goal is to make the tensor type-safe. We add this thing here, So a tensor has a type parameter called axis. Axis is a tensor axis descriptor. It describes the semantics of each axis. It is basically a tuple of singleton types. They are labels to axes. We should see it later. So all operations and tensors are statically typed, like addition, subtraction, matrix multiplication, sum over reduction, axis reduction, whatever. There's a lot of these I'm going to introduce later. The result types are going to be known and compile time, so IDEs can help programmers. You don't need to remember them. If you just forgot the type of one tensor, just move your mouse over it. IntelliJ will just pop up and show you the type. And also, errors would be thrown out at compile time instead of runtime. So in Python, sometimes you just starting running a program on the grid for a night, and the next day, in the morning, you're looking at it, it just failed with some type errors. So, so we want the compilation failure when operating incompatible tensors to be thrown out at compile time. So, so this image here, would be going to typed as float tensor of width height channel as a tuple. Width height and channel are just singletons. So you just define singletons. So these are just labels. They don't have any actually meanings to them. They're just singletons. They just serves as labels to each axis. And this thing, the sentence would be just typed as float tensor of word and embedding. This is a tuple. So we want to make several type safety guarantees. Operations on tensors are only allowed if their operand's axis makes sense mathematically. For example, a tensor of A plus tensor of A, good. They are the same thing. So a vector could be added with a vector. But tensor A plus a tensor of AB, which is a matrix, compilation failure. Or tensor A plus tensor B, compilation failure, because they're not talking about the same thing. Those vectors are not semantically compatible. Another thing is like tensor A plus tensor AB is actually usually runnable and does not throw any error in Python programs, because Python has this thing called implicit broadcasting. So if tensor A plus tensor AB, the A got expanded into the same shape of tensor AB with it's just repeated. So this is just, the type is completely wrong, but still runs. So this creates a lot of problems that you don't even know. This is addition. For example, another example would be matrix multiplication. If I want to do matrix multiplication between two vectors, no. So compilation failure. If I want to do multiplication between two tensors of the same shape, no. It doesn't make sense at all. It has to be that the second axis of the first tensor and first axis of the second tensor, when they are the same, you can proceed with matrix multiplication. And you got a type, result type of tensor AC. So more complicated example would be the so-called axis reduction operations, where, for example, you want to do this. This is a tensor of 3 dimensions. I want to sum out the second axis. This is called axis reduction or marginalization in machine learning literature. So it becomes YIK, the J axis is gone. So in Python, so you write like TensorFlow reduce sum x dim equals 1. So I don't know what dim equals 1 is. Sometimes if you swap a little bit, it became dim equals 0. You have to track the indices. That's very frustrating. So I plan to do it like this. If x is a tensor of A, B, C, 3 types, we sum along B. This sum along B is it's an operator, and applied on x, we got tensor of AC. If we sum along D in x, compilation failure, because D does not occur in the axis of tensor x. So we want to do these. So here we see that the tensors here are all tuples, and they are hard to actually reason, but they look good. Actually, behind the scenes, there are H-lists. H-lists are much easier to manipulate, so you can use type-level manipulations in shapeless, or you can write your own. But tuples look better. I don't think people would like to write a tensor of A, colon, colon, B, colon, colon, C, colon, colon, H nil. It just looks worse. So we can use tuples, and we could use the generic and the tupular in shapeless to do the bidirectional shift. So that's not a big issue for us. Okay, so let's look at the, so now we have tensors now. So we're now going to look at the computation graphs. So as we said before, every deep learning program is a composable program formed by little parts of it. So like this is a computational graph. So in Scala, we would very naturally represent it as a generalized algebraic data type, as in GADT. So we have a seal trait expression of X, which is a symbolic expression of anything of this, whose type is X. So we have input. So this is the input nodes that we feed in when running the program, when interpreting the program. And this param. So these are params. These are so the parameters of the whole thing that is going to be learned by the machine learning system. It's a var here. So it has to be referentially not transparent because we have to do successive updates on it. If we make it a val, they're going to allocate a lot of memory on GPUs and whatever. So it's a mutable variable here. It's going to be mutated every round. So it has a tag grad. Grad is a type class saying that this variable is differentiable. So we're going to talk about that later. So there's param. And there's const, which is just something like a constant in the program somewhere. And there is just these apply thing. So app1 is an expression of type Y that is formed by an expression of X, then applied on an operator of X to 1. So this op1 is differentiable. So so you can learn instead of a non-differentiable function. There's app2, that's application of over and binary operator applied over 2 expressions. And there's app3 and so on. So basically, the class diagram, we have something like this. So every expression could be any of these types. So this is a GADT here. So when we are doing the forward and so we're interpreting it or we're training it, so we can do pattern matching on all of these. There are some slight problems with GADT pattern matching in Scala, the types, but these are minor issues. So we saw operators here. So operators here, they just cannot be a simple function. We need to do differentiation against them, so they have to be differentiable. We have to specify in the op of how differentiation works in it. So op1 is something like this. So apply, given an expression of X, we result in an expression of Y, where it's just a wrap this created this app1 node would put this operator itself in it. And there's forward computation is just, oh sorry, this just should just be fx just compute the function, and backward dyyx is just doing something like this. So we want to compute the derivative of the final loss with respect to this variable by using another the gradient of y and transform here. So this is what is done in deep learning. So this is a crucial operation here. You have to encode it in the op class. This is op1, and in op2, you're going to have 2 backward functions here. You can propagate the gradient through the x1 and also through x2. So that's op1 and op2 that you can generalize to op_n. And so let's take a look at how this computation graph is interpreted by the program. So this is a program we have now. This is an app node, app2, 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 and every app2 is accompanied by a op2, that's the operator there. So the whole thing, the interpreter itself has this type. So it's given an expression of A, that's the final expression, that we compute the value of it, that's A. So this is a natural transformation. With Cas, we type it as expression to ID. So this is a general interpreter on the expression type. So interpreting the computation graph, this is very easy. So basically, we do a recursion and a pattern matching on these. So to get the value of L, we get the value of Y and get the value of this. To get the value of this, we get this and this recursion. So we can also do it by, so this is the a standard way of doing it. So backward computation is when we want to get the gradients of the parameters. So to learn the parameters, we need to have gradients on top of these so we can mutate these variables. So once we have the loss, so from the last node, that is loss node, we propagate the gradient back through the backward operations we just said in it. So it is for each node x, we're going to compute the gradient of loss with respect to x, and that is just the common theme called automatic differentiation in other languages like Haskell. We have programs like that. It's exactly the same thing. Okay, so that's forward and backward computation. So next we're going to talk about operators. So we have seen there's a lot of operators. We haven't, so this is a general scheme on top of computation graphs. We haven't applied them on type-safe tensors. Now we're going to apply them on type-safe tensors. First, I'm going to introduce operators versus modules. So operators is just the operator assigned on each node. It can be directly computed using a forward method without interpreting it. And there's also modules. So it's a subgraph that you have to use an interpreter to interpret. So basically, so this line, so this block of this gray block box is a module, and everything, this little minimal unit is called a operator. So in this Nexus library that I wrote, we all of these just they inherit the same underlying supertype that is func of xy. It's basically an type alias of expression x to expression of y, and it has two major subtypes. Op1 is so you can do it at the value level instead of the expression level, and module 1 is you have to do it on expression level, and it has a set of parameters in it. So, for example, this module, you have the parameters to be a set of A and B. So now we have saw that op xy only applies on one type x, so it can only be applied to x. But for example, like addition on tensors, it applies on tensor of A, it applies on tensor of B, tensor of AB, tensor of ABC. It all applies, so it has to be polymorphic to the type. So we create something similar to shapeless poly1, that is the polymorphic function in shapeless. So a polyfunc has this thing. So a polyfunc has this type f here that is just an implicit here. So it is a predicate that proves this operator can be applied on x. So we have a ground operator that, given the proof, generates the non-polymorphic, this lowered it to the grounded version, and then we can apply it on it. So basically, if we want to apply this polymorphic function on the expression of x, we need a proof that is doable. And if we had the proof, so we can just ground it and then apply it on x. So f here is very similar to shapeless case.aux, which is the proof that this polymorphic function operates on x. So this apply function is only applicable when op of f xy is found. If found, the result type is expression of xy. So this is an arbitrary type level predicate. So this is basically an instance of compiling as proving. This is Curry-Howard correspondence. If we found an implicit of xy, it means that the proposition, the type level proposition fxy is proven. So thus we can encode any type of type constraints into the system. So the compiler proves the correctness of the program for us by finding the implicits. So let's look at some of the examples here. So this is a Polyop, which is a, I just introduced the difference between an op and a func. Func is more general. Op is just depending on just a minimal unit that's directly callable. So we also have polyop and polyfunc. Polyop, so the f itself is an operator. So yeah. And the good thing is we can have an implicit not found on the trait f. So if you apply the function on something that is not compatible, the compiler will throw a very nice message to you. It says this operator cannot be applied to an argument of type x. So you can do, it's very user-friendly if you use a, yeah. So for example, add. So if we know if two variables of the same type and both they can be differentiated, they can be added. So basically we want to encode this preposition for every type x. If x is differentiable, we know that you can apply x and you can apply add to x, and the result type is x. So this is the predicate that we want to prove by the compiler. We do it like this. So implicit def f, if x is a grad, we got a fxx. And we actually encode the actual behavior of the function add into it. So forward is x and x. Backwards, we just pass the gradient through. So, so in this way, so add can be applied to any two expressions of the same type when it is differentiable, if it's not a thrown exception. So this is add. A second example is matrix multiplication. We know that two matrices can be multiplied when the second axis of the first matrix coincides with the first axis of the second matrix. So we want to encode this predicate in the type system for tensors of TR. So here T is a tensor type, R is float or double or whatever. So is real tensor K is just a type class that it's similar to a vector space in Spire or something. It's just a tensor space. So we know that T of AB and T of BC can be multiplied to get T of AC. We want to encode this thing in the type system. So we got this. So basically, we require that T is actually a tensor of real variables, and then we encode this. So this is the actual implementation of it. So this is matrix multiplication. So some more complicated examples like axis renaming. So sometimes we want to rename an axis, like database, we can rename a column. So we want to change the type of in A to B in X. So what we want to do is something like this. We know that T is a tensor. We don't care if it has a real in it. It's just a tensor will be okay. And the axis of X is A. Remove axis U, add axis V. We got B. So if this is true, we know that if we rename TA, we can rename TA to TB. If we want to rename, oh sorry, this should be renamed U to V here. Okay. So we do this. So we have a replace.aux. So this is a type level predicate that proves if I remove U from A and then add V, it gets into B. So we can code this in a shapeless style. So so we can do this. So if we do this, the rename function can only apply to A if this is satisfied. Or sum along axis, as we talked about this earlier. So we need more complicated things here. We need some Indexoff. So so this thing proves that N is the U is the nth type in A, where A is H list, and remove add is we remove the nth type in A, and that results in B. So we want to prove this thing is if T is a tensor and A removed U is B, then I can sum over U. Then so we can sum over axis U on the tensor TA, and that gets into TB because A is removed here. So here the axis J is removed here. So this is going to be we can encode this type relation in this format. So if we had a tensor of ABC, we sum over B, and the compiler would infer that result type is tensor of AC with the B removed by this relations here. So the index of and remove add is not there in shapeless. We need to add them myself. We need to write them ourselves. So basically, we want to prove these two things: index of x t, and x is the zeroth type in x is the zeroth type in x and t. And if we know that x is the ith type in t, we know that x is the I plus 1th type in h concatenated with t. So this is recursive implicit, commonly done for shapeless. So we encode it like this. So, so for nearly all neural operators commonly used in practice, like the things I talked about earlier, like addition, subtraction, or like various like sine or log, exponential or matrix multiplication, reduce over axes, and like more complicated things like convolution neural nets. They can all be encoded in such a type-safe way. But to make them run fast, so we cannot just run them in the JVM. It's going to be very slow. So we need some native C or CUDA integration. So CUDA is the framework that runs tensors on GPU that's highly parallelized and it's very fast. So we don't want to do math in JVM, so we have to integrate with native code in C or C++ through JNI. So the underlying C+ code is we're going to bridge them to the JVM using Swig. So we could have a CPU backend that's run everything on CPUs using BLAS or LAPAC from MKL, libraries like these. And we can also run things on CUDA by using cuBLAS and things like these. We could also have an OpenCL backend, but no one's working on it right now. So let's look at an example of how these Python libraries do this. This is, for example, you're using PyTorch as an example. So this is BLAS and LAPAC. It's underlying C library, or sometimes coded in Fortran, sometimes C. And they have this torch, and torch NN lies on top of it. And also for the CUDA version, there's torch CUDA NN. NN is a neural network, lying on top of it. And then bundled a dynamic linking library. It's SO on Linux, dylib on Mac, and DLL on Windows. So, and then generate a Swig bridge, and then we create a Python wrapper on top of it. This is what people do. So we copy this framework to Scala. So, and in Scala, we could actually have multiple backends. So we can, so for a tensor to be able to run on any of these, so we just need a is real tensor K type class. So this type class says that how we can run these. So we can use multiple backends. So we can import a CUDA type class and then runs on CUDA, and import a CPU type class, it runs on CPU. So it's a very flexible way of using type classes. And because we want to be, because there's loads of work by the Python guys, they have written up this C and C++ cores. We're going to just use their cores, their C libraries, and just use Swig to generate them and to call them from Scala. So we are reusing these C libraries coded by these Python people. Okay, so the next topic I'm going to talk about is a more complicated thing, is like neural networks with dynamic structures. So what we have earlier, all the neural networks, the computation graph is fixed for all samples. But that sometimes is not the case. Well, for example, this is common in natural language processing, where a sentence could be of variable length. A sentence could be short, a sentence could be long. So the computation graph actually varies for each sample. Sometimes we use this thing called a recurrent neural network, and Scala people should be very familiar with it. This is just a fold operation. Yeah, but you can fold over different lengths of the sequences. So the program, the computation graph, is actually different for each sample. And that creates some problems. There's like more difficult problems, like you could have models that operate on syntax of natural language. So they have every sentence, we're going to have distinct syntactic structures, like the cat sat on the mat. We have a noun phrase here, have a preposition phrase here, verb phrase here, and a sentence on top of it. So the tree for each sentence will be different. But there is this paper from Stanford that does sentiment analysis on sentences that gives the structure. They construct a neural network in the structure of this and then compute all the way through the root of it. It's basically a catamorphism in category theory. So these are more complicated case where the neural network structure change with respect to the sample. So let's take a more complicated example at a machine translation. People call it seek-to-seek. It's like given a sequence, returns another sequence. So it's a sequence transduction job. For example, here we have a German sentence, Das Haus ist klein. So we'll first do a scan operation on top of it, and the backward scan. And then we do something on top of it that just merges these two. So this is called the encoder in literature. So that encodes the semantics of this sentence into some form here. And then we use a generator that generates the English translation, the house is small, by at every step the neural network would look at these encoded information and then generate the next word, the, and all the way until end of sentence is found. So this is a dynamic structure. The structure for each sentence changes. So in Python, it's very hard to do it, but people still do it. This is hundreds of lines. But we could easily see, for us familiar with functional programming, this program is very functional. This is very easily expressed in functional terms. This is scan left, this is scan right. This is like zip with concat. This is unfold. So we are planning to create, in Scala, create a DSL that writes a neural network like this with these functional primitives. So, so here we have introduced the notion of dynamic computation graphs, where the computation graph for each sample changes because of the shape of it. So there's the static graph that we construct the graph once, interpret later. So in that framework, it's difficult to implement dynamic neural network like the neural translation there. Or there's dynamic graph. So you compute as you construct the graph. Every time you create a new node, the actual value in that node is computed. So that's the dynamic approach, but you lost the ability to do runtime optimization. Sometimes you want to create a graph lazily, and then you can optimize the graph before running it, before interpreting it. So there is a spectrum. So static and dynamic. The current approach, the current landscape of the Python community is like TensorFlow, Caffe2, and MXNet is static graphs. PyTorch, Chainer, and Gluon is these dynamic plots, dynamic. So, and there's Dynet in the middle. It lazily creates graph for each batch and then do runtime optimization and then run. It's like in the middle. But I propose something that gives user more control, that users can control whether it is interpreted lazily or eagerly. So we add something like this. So for each expression, we get a value function in it. So you could compute the value of an expression if it's in a scope of implicit computation. The computation is this forward interpreter that we discussed earlier. So in a computation scope, you can get the value out of it. And when you get the value out of it, the interpreter is forced to run until this node. So when you build a graph, it's lazy, but if you call value, you're forcing the interpreter to evaluate it. So it's going to be very versatile. So you can switch between these. For example, this is the DSL I constructed in the library that we can do a multi-layer neural network. So X is first pass it to the first layer, pass it to a function, and pass to the second layer, pass to softbanks. Every step of these is type safe. So, and the loss function is a cross entropy between these. So this is a standard neural network. So this constructs the computation graph declaratively with no actual computation executed. This is a lazy graph. So I create this thing called given is a clause that you can feed the values, actual values, into the computation graph. X and Y are inputs to the graph, and we feed them into it. So in this given clause, where there's an implicit computation is instantiated. And so in this block, you can call value. So you can, if you call value, the whole computation graph here is executed. So we can get the loss value out of it. But if you do loss.value outside the given block, it doesn't work. So you can control. So you can also build your network in here. So that's dynamic. If you build your network outside the given scope, it's static. So it's just it's versatile. You can switch between these. I think this is much more flexible than the Python approaches. So that's basically what I've been talking about today. So there's a lot of future work to be done to make this a fully fledged deep learning engine. We would like to do automatic batching. That's fusion of computation graphs. So sometimes, because GPUs are highly parallel. So sometimes we want to like concurrently run a lot of samples on top of it. So for current libraries, well, most of the current libraries, this is done by hand. So for every sentence tensor, like for example, a sentence or an image is width, height, channel, you add another batch to it. So you've got a 4-dimensional tensor that is batch, width, height, channel. So you manually create another dimension on top of it. So it's bothersome to write, and you have to keep track of another axis. So we propose to do automatic batching. This is actually already done by the DINET library, but so you create a bunch of computation graphs, and you, before running it, you fuse them into one graph, and so before run, your system decides which operator can be parallelized, and you can merge these operators into one and then send to the GPU to run. And there's complete GPU support. We have a preliminary GPU support now, but we don't have any garbage collection. So these things, because these memories are allocated by JNI, so JVM doesn't track these off-heap memories or GPU memories. So there's going to be a memory flow. So I don't have a garbage collector right now, but that's part of future work. And we probably also can do distributed learning through Spark. So in Spark, so we could integrate this whole framework with Spark to do a distributed machine learning on a grid. So help needed. So if you're interested, you can just I'm happy with pull requests. So so question and answers. Thank you. Okay. I actually raised the issue of naming the axis in Python, but people, with a string in Python, of course, not with a type, not with a singleton type. But people don't like it. People think it's just we are fine with what we have. So okay.
So one question. So in your HList code, it looked like you were sort of using the HList like a set. So it seemed like the axes had to be distinct, because you were like saying the index of law only works if you don't have duplicates.
Yes.
Is that something that you are enforcing, or is that just a convention you want your users to follow?
It's just a convention. It's like a database columns. So you don't want a database with 2 columns with the same name. Yeah. Right. Yeah. Okay.
Is it possible to stop the computation and resume it at some later point?
That's checkpointing. That's for future work, but yeah, that's planned. Yeah. Okay.
Have you found mistakes in other people's Python code by translating it into your own?
Excuse me?
Have you found mistakes in translating other people's Python code?
Translate the code into Python?
No, translating Python code into this.
It's harder because this has more type information in it. So yeah.
Have you found other people's mistakes though?
No. It is. Yeah, that's so let me see. So axis here. So for right now, the axis is just a label here. We might extend it to width and then a tuple and a number, because because of like this, what is the SIP number that does singleton types. So we can have an int in the type. So we can just for that way we can enforce the size of the axis in the type system. Yeah. Okay. Python code or Scala code? Yeah, I can. Yeah, this code is quite clear and it's completely readable. Yeah. Yeah.
Integrating this with ONNX?
Excuse me?
Have you considered integrating this with ONNX?
Yeah, I'm considering that, but there's problems with Onyx because Onyx is untyped. So I can serialize the whole thing into Onyx, but I'm not sure how I can deserialize it back. Yeah.
Did you look at other languages for picking Scala?
I've been working with Scala for years, and yeah, Scala has this shapeless in it that is like, I don't know how to do this without shapeless. So, yeah. Okay.
If you had more independent typing, so something, think like what Idris has or something like that, would that have solved any problems with the design of this library?
Oh, I'm not sure because the typing constraints is rather complicated in a lot of cases. So this is the only way I can work up with it. Or yeah, probably could be done with C++ templates. With this, the C++ templates, you can do this partial specialization. You can have multiple partial specializations of template, and I think that's very similar to like implicits actually. Okay.
Mind tweeting out these slides?
What?
Do you mind tweeting out these slides?
Oh, no problem. Yeah. Thank you.